All right. Welcome students to the lecture 7. Um, in the last lecture, what we have discussed is basically the number of electrons that can be accommodated in the lowest band, right? And what we have found out is that if n is the number of unit cells or primitive unit cells in the one-dimensional case, then 2n would be the twice n is the number of electrons that can be accommodated in the first band, right? So now let us consider a hypothetical solid, one-dimensional solid, where so one-dimensional solid, basically it's a linear chain of atoms, right? And where the electrons experience those periodic potential that we have discussed under the chronic-Penny model. Now let us consider a case where each atom provides one electron, right? So these are monovalent, one free electron, valence electrons. So these are the monovalent atoms, right? So if there are n number of atoms in the solid, then the total number of electrons in the system is n, and therefore the band would be half filled, because twice n is the number of electrons that can be accommodated within the field, within the band, right? So that's what I'm showing here. This band, right, which gets flattened at the zone boundary, right? So red color is the line that is the Fermi level. So that is the maximum field energy state, right? So that is for the one electron per atom case, monovalent atoms. So what happens is that now there is an interesting consequence of this. The consequences that these electrons, if they experience some electric field, for example, right? So they gain in energy. So because of the gain in energy in this field, so they would like to move to the higher states, right? These states are available for them, and therefore the electron starts conducting, right? So therefore these half-filled bands, these are metals. Okay. Now let us consider 2 electrons per atom, right? What happens if an atom has 2 valence electrons, right? So if there are again n number of atoms, then the total number of electrons is 2n, and therefore the band would be completely filled, right? So this band will be completely filled, and then obviously the next band, so beyond this band there is forbidden gap, right? So therefore if these electrons experience some electric field, for example, they can't move to the higher energy state, right? Because they don't have any state there. There's a forbidden energy gap, and therefore they don't conduct. So therefore this, in this one-dimensional case, divalent atoms, solids with divalent atoms would be insulators. Okay, so therefore field bands means electrons do not have any of this state to move to, so therefore they are insulators. Okay, so this is the consequence of this, right? I'll come back to that when for the two-dimensional case. Now before that, let me discuss the reciprocal lattice. I'm not sure if you are ever have come across this, or if you have been taught this reciprocal lattice earlier, but so this has an interesting consequence. If you consider the space, not the real space, but the inverse, that is the reciprocal space. So let me clarify this point further. So if all of you know, you are students of mathematics comparisons, all of you know that if you have any time varying signal, right, you can write it in terms of the Fourier components in the frequency domain, right? So similarly, a periodic lattice, right, can be properties of this periodic lattice can be explained in terms of the lattice points, which is in the Fourier space. So that is the inverse lattice space, and that's what is called reciprocal space. Okay, So that means if you have a perfectly periodic crystal, for example, the periodicity can be given by just one point. So this multiple periodicity, you can have multiple points, and these points can describe the properties of this lattice, of this solid. Okay, so therefore reciprocal lattice is important. So these have dimensions of inverse length. Okay. So now let us, so the T, if you have a direct lattice, which is governed by the translation vector T, where T equal to N1A plus N2B plus N3C, I'm sure you have studied these things. So where A, B, C are the primitive vectors in real space, right? So if you have a translation vector in real lattice given by T, then one can define a reciprocal vector in the reciprocal lattice, which is given by G equal to, G is just a vector, again this is in the reciprocal space, so this is the reciprocal lattice vector. G equal to H A star plus K B star plus C K L C star, where A star, B star, C star, etc. are the primitive vectors in the reciprocal lattice. Okay. And so these are related, this S star is related to the reciprocal lattice vectors are related to the direct lattice vectors, primitive vectors, by these relations. So B cross C by A dot B cross C, B star is given by this, and C star. So one can write this, one can find out this. So if you know the direct lattice vector, for example, right, if you know the primitive vectors in the direct lattice, let's say A, B, C, then you can find the reciprocal lattice. Okay, so and they satisfy this relation. So S star dot A equal to twice pi, right? So similarly, B star dot B is twice pi, and C star dot C is twice pi. Okay, so this twice pi, in some books you may not find this 2 pi factor. This 2 pi is taken into consideration to numerically make it equivalent to the wave vector space. Okay, so wave vector we are familiar, we have been discussing all along about k values. So k is the wave vector. So to make it equivalent to this, 2 pi factor is included here. Okay. Alright, so this is about the reciprocal lattice. Now what happens, let us see. So let us consider an oblique lattice, which is A and B, given by these primitive vectors A and B, right? It's an oblique lattice. And then the reciprocal lattice would be A star B star, where A star would be perpendicular to B star, B, and B star would be perpendicular to A. So this is given by the definition that we have discussed in the last slide. Right, so you can now if you, as I said, if you know A, B, etc., then you can determine the reciprocal vectors, reciprocal lattice points using these vectors A star, B star, etc. So this is in the two-dimensional case for an oblique real lattice. Okay, so that means to summarize this, that what we now understand is that for any direct lattice in the real space, right, in the three-dimensional case, T equal to N1A plus N2B plus N3C, which is periodic. The reciprocal lattice is periodic and is infinite, right, and which will be given by these values. Okay. Alright, so once you can find out the reciprocal lattice vectors, then you can determine the Brillouin zones. So you remember in the last class I have discussed the Brillouin zone. So you remember this Brillouin zone, you have discussed the zone. Let's say if you consider the first Brillouin zone, for example, the zone at which you see the discontinuities in the energy, right? Let's say pi by A2 minus pi by A for one-dimensional case there. When we plotted this E versus Kx. For kx equal to pi by A to minus pi by A, that is the zone boundary, right? So this is the zone boundary of the first Brillouin zone, and in the reduced wave vector scheme, you have seen that all the second band, the third band, etc., that can be all shown within the first Brillouin zone, right? So this is called the reduced zone. So now how can we find out the Brillouin zone in case of two-dimensional case? Okay, so there is a simple way to do this, right? Once you know the reciprocal points, right, so reciprocal lattice vectors and lattice points in the reciprocal lattice, this is the two-dimensional case, right? So you have determined the reciprocal lattice points given by the expression that I have just shown earlier, right? Now these are the reciprocal space. So this each point, red points here, denotes k values. Okay, k values here. Now to find the Brillouin zone in this case, the first Brillouin zone. So Wigner and Seitz, they have shown actually a very simplistic picture, simplistic way to determine this. Okay, so this is the primitive lattice in the reciprocal lattice. Reciprocal space is the first Brillouin zone. So primitive lattice here, how do you find out? The idea is that this is a procedure actually. You take a central point, this is a reciprocal lattice point, and then connect to the next nearest neighbor point. Okay, so with these vectors, and then you draw a perpendicular bisector between these points. Okay, so you see that each central point is connected to each nearest neighbor point, and then the perpendicular bisector, and then you join them. So this central region shown by this hexagon is distorted hexagon is the first Brillouin zone. Okay, so similarly you can determine the second Brillouin zone. Now for the second Brillouin zone you have to go to the next nearest neighbor. Okay, so you connect the next nearest neighbor to the central point, and then you can determine and similarly you draw the perpendicular bisector, so you can determine then the zone given by this would be given by, called the second Brillouin zone, etc. Okay, so this is an example for an oblique lattice, and now let me come to I'm sorry, there is something happened in the picture here. So this is the square lattice, again in the reciprocal space. So you know for square lattice in the reciprocal space, the direct lattice is also a square lattice. So basically, if you have a direct lattice, real lattice, right, in the real space, the lattice points have square symmetry. Right, in the two dimension, then the reciprocal space is also square. But that you can calculate actually with this and with the formulas that I have given, right? And now you draw the Brillouin zone. Okay, so there has to be a central point in the yellow part, right? So basically what we are seeing here is actually 1 2 3 4 5 6 7 8 and 9 points altogether in these 9 reciprocal lattice points here. And you take the central point, which has unfortunately been covered by the yellow square here, right? And then you join the next nearest neighbor, and then draw the perpendicular bisector that gives you the square zone. So that is the first Brillouin zone. For the second Brillouin zone, you connect to the next nearest neighbor, right? So next nearest neighbors are at the corner. So and join the central point to the corner point, and draw a perpendicular bisector. So what you get is the blue region. So blue region beyond the yellow region, this is the second Brillouin zone. Okay, so similarly you go on to the next one, so that will be then the third Brillouin zone. So this space is kx ky space. Okay, all right, so this is a simplistic case for the Brillouin zone, the first Brillouin zone, second, third, etc. Brillouin zone for the square case. I'm sorry, these 4 triangles, they have got distorted actually just during conversion, I think, to this mode that I'm presenting now. So they will actually cover those triangles, white triangles. Okay, so they will cover similarly. Okay, oh, so here also it has come. So now let us consider this. Okay, let us consider this the leftmost picture again. Okay, what you see here is the red circle here. What I mean by this is you consider a monovalent atom, solid of a monovalent atom, right? So within and this is a free electron picture. So if you consider a solid monovalent atom, then as you have figured out, monovalent will give you half filled band, right? So therefore the first Brillouin zone is not completely filled. Okay, so it is the half filled band. So how do you why I'm taking this circle? Because we are considering free electron picture, so that means energy would be given by h square k square by twice m, right? So if it is half filled, the highest energy level will be given by the k values corresponding to the Fermi surface, right? So this is the Fermi wave vector that you have determined earlier. right? And you remember that we have found out a relation between Fermi wave vector and carrier density. So if you know the carrier density, you can determine this, determine the Fermi wave vector, and then you can draw the Fermi surface in the free electron picture, which is a in the 2 dimension it is a circle, right? In the 3 dimension it is a sphere. Okay, and now this is, since this is one monovalent, as we have just discussed, this will be half filled, right? So you see that the Brillouin zone is not completely filled. Okay, so now let us discuss this second Brillouin zone. Discuss the case for the divalent atom, right? In the 2 dimension now. 1 dimension we have discussed, this is in the 2 dimension. So what happens is now for the 2 dimension, right, you can you draw this Fermi surface, right, and you can again free electron picture. So you can consider Kf, you can determine Kf values, and if you know the Kf values, then you can draw the Fermi surface again here. So now it is, because it is divalent, right, your Kf depends on the number of electrons, right, in a certain way that you know already. So now you draw the Fermi surface, which is again is circle in this case. Now you see that with this Kf, the Kf values, this Fermi surface actually crosses the first zone and enters the second zone, right? So the Fermi surface enters the blue zone in the 4 cases, in the 4 triangles. So that means it is moving from the, so that means what it means is basically that you have some electrons in the first Brillouin zone, first band, and also in the second band. Okay, going to the second Brillouin zone. All right, so now why it is important? It is important why we are doing this. We are trying to understand actually. You see that in the 1 dimensional case we have said that the divalent solids are insulators, right? No, but in 3 dimensional case, in the real case, we see that there are many divalent atoms, like calcium, barium, etc. Those things, these are all metallic. So if you look at the periodic table, so these are all metals. So how do you understand that? Okay, so you can understand that from this picture, from the Brillouin zone band structure here. So now let us consider it elaborately. So I am considering the middle picture now. This is the first Brillouin zone, right? So first Brillouin zone, your Fermi surface crosses this at this point. So you know the Fermi surface is the first band is not completely filled, as you see, right? As you see, first Brillouin is not first Brillouin band in the first Brillouin zone. This is not completely filled, so there are some empty pockets there at the corners. Recording করছিলাম আসছি. Okay, so the there are some disturbance. So what I mean is the first band is not completely filled, as you see, right? Whereas on the right hand side, on the right side, you see that this is, now I'm showing that this part of the Fermi surface which is crossing the first Brillouin zone and entering the second Brillouin zone. So only the second Brillouin zone is shown here. Now some part of the second Brillouin zone is occupied now. So that means you have electrons now in the first Brillouin zone and also in the second Brillouin zone, or the second band. And the first band is not completely filled, right? So that's what you see, and you have some electrons in the second band. Okay, so now, so this is the free electron case. What happens if you case a real case? So for example, if it is a if you have a band electrons, so you know the band electrons, what happens is at the zone boundary these curves get flattened, right? So in the 1 dimensional case you have seen that. This is the 2 dimensional case, right? So the top 2 figures are the same repetition I am showing. This is for the free electron case, and the bottom 2, these are the band structure. These are for the band electrons, right? So in the band electrons, what changes in this case is that at the zone boundary the curve gets flattened, right? Instead of a simple parabola, you know, for the free electron case, now your curve is getting flattened at the zone boundary. So that's what you see. And for the second Brillouin zone, you see that this is also flattened, but now because of the reduced zone scheme, because K values are periodic, so they can be folded, right? So those those states in the first Brillouin zone, in the second Brillouin zone, they can be shown in the second Brillouin zone. So that's why I'm showing it in the folded scheme. Okay. this is what we have learned from the band structure, and actually this is an application. So from this figure, now what you see is that now what happens is that electrons actually, because the band is not completely filled, the lowest band is not completely filled, if you apply an electric field, for example, the electrons, when they get higher energy, they have states to move into, right? So therefore they can start conducting. So therefore these are actually metals. So this is how you understand the metallic behavior in the divalent case in the 2-dimension, or also say true, this is true also for the 3-dimensional case. 2-dimensional case is simpler to visualize, so that's why we're discussing this. So so the statement I'm making is that divalent metals in 2 dimensions, divalent solids in 2 dimensions are metals. Okay, they conduct electricity at t equal to 0. Okay, so I'll stop recording here because I see that there are problems with the large more than 30 minutes kind of videos. I could not upload this, so I'm stopping it here, and then I'll start the next class soon.